So in this lecture we'll quickly rush through the drain feedback bias, which is another kind of feedback bias to maintain constant ID. So drain feedback bias in a PMOS transistor. Drain feedback bias in a PMOS transistor. And eventually we look at what is called the current mirror and PMOS current mirror and so on and so forth. Okay, so if you want to look at the drain feedback, we know that we compare the currents at the drain of the transistor and feed it back to the gate. Okay, so you sense at the drain and feedback at the gate. This is drain. Okay, and this is what we called as drain feedback. And how an NMOS transistor we is being constructed is something we know it very well. For an NMOS, let's say for an NMOS, it looks something like this. You have the NMOS transistor, and this is the drain, this is the source. So we basically compare current at the drain, meaning drain connected to VDD. You put a current source at the drain in this direction. Let's call it reference current I0, and the current flowing like this is ID. You compare this current being I0 equal to ID. Okay, and then you feed it back through the gate. So you fed it back through bias resistor or directly, or using some incremental positive incremental gain, it doesn't matter. And this particular feedback itself establishes the bias at VG and a bias at VD. Okay, and because of this transistor is always in saturation, because drain and gate are anyway the same, and the condition for saturation is VDS to be greater than VGS minus VT. Okay, this is something that we established already. And then you connect your source and you connect your load here. This is what we had done and we had discussed in detail also. Now, going by the same logic that we had discussed last time, how do you convert it to the PMOS circuit? Okay, it's very straightforward. You reverse the polarity of all the sources and then replace this transistor with the PMOS. That's it. And while doing so, do not consider the source and load for the moment. Okay, so if I do so, I'll get a situation like this, and then reverse the circuits. Okay, reverse the draw the circuit upside down. That's what we said. So if I do so, then my VDD will stay here only, and I'll have my source connected to my VDD, and my drain is to be compared with the current ID. So I'll have my I0, and this is the feedback node because this is a drain, source and gate. And this transistor also is in saturation, and the condition is that my VSD is greater than VSG minus VTP. Okay, and it's always true, and this potential is connected to ground. Okay, so and then I add my source here and then load here, and source will be added to the gate. Okay, let me do it like this. Okay, so how do I know what is this potential, the gate and drain potential? So for the case of NMOS, VGS is equal to, which is the gate drain potential or gate source potential. S is anyway grounded, so this is equal to VG, which is equal to VT plus twice ID by Kn W by L. So what about for this is for NMOS, and for a PMOS, I know that I will have VSG given by the same relation, which is nothing but VDD minus VG, because VS is VDD. Okay, and from here I can obtain my VD, VG all the time, so which is equal to VT plus twice ID by Kp W by L. Okay, this is what you would get, and this potential VG is the potential at this point. Okay, and you obtain VG by doing a simple algebra. So it's VDD minus VT minus twice ID Kp into W by under root. Okay, so yeah, so this is this potential at this point. Okay, So you know how to construct the circuit of PMOS, how to establish the DC operating point, and only thing that is remaining is small signal analysis and small signal capacitance constraint, which I am not going to do now because it is exactly the same that we have done for a NMOS, and you can go back and refer to that and try to relate it here. Okay. Now obviously if I have a situation like this, then this transistor will always remain in saturation. So drain feedback transistor always in saturation, both NMOS and PMOS. Okay, we know that this is true for N and PMOS. So if it is the case, then what is the advantage we have? We can actually use it to mirror currents. That is what we said for an NMOS case. So here also we'll be doing the same. We'll use this particular case to mirror the currents. Okay. So how do we do the current mirror is something that we will see now. Okay. So NMOS current mirror, I'm not going to show it here, but you know how it is done, or let me show it. It doesn't harm me to show that. So NMOS current mirror is where I'll have the same transistor setup, which is I naught, and I'm comparing this current to my ID, and then I'll make sure that I have this feedback established. Okay, if this is the case, then I can extend this particular gate voltage to other gates so that this voltage and this voltage are the same, and if these transistors M0 and M1 are exactly matched, okay, if they are exactly matched, then as long as I keep my VDS greater than VGS minus VT, okay, then I'll have a current that flows here equal to I0, because this also equals to I0. Okay, so this is the mirroring concept, and then I'll extend to another case where I'll choose a W by L here, and this will be 2W by L if I choose it so, and then maintain this VD also at this particular value greater than VD is greater than VGS minus VT of this transistor. Okay, then I'll make sure my current is 2I0. So this is what I called it as NMOS current mirror. Okay, for as far as the PMOS current mirror is concerned, it's exactly the same thing, just that we will use a PMOS transistor. These are all NMOS transistor. For a PMOS transistor, we know you use this setup. Okay, so let me draw it in this way. Sorry, this is the source, this is the source, and this is the drain, and you establish a feedback here, and the drain current should be sensed to be equal to ID, so let's call it I0. Okay, so this is what I would do. Now if I extend this particular gate voltage, or this is the gate, and then bias it to this transistor, and as long as this source is also equal to this voltage, okay, which is at say VDD, this is VDD. Similarly here all the sources should be grounded, then only their VGS will be same. Okay, VGS is to be same for all these transistors, it's a mandatory criteria, then only current will be same if you keep the transistor drain voltage so that this is operating in saturation. So here also VG is the same, so maintain VS also same. In that case I'll have this current ID is equal to I0 if these two transistors are identical. M1 and M0 will have same W by L and so on. I should just make sure that I keep this particular drain voltage, okay, in such a way that VSD of this transistor is greater than VSG minus VTP. Okay, and I can extend and scale the currents and so on and so forth. This is very straightforward for me. Okay, and so let me also do that. If I extend this gate voltage, and then if I say that this is my source, which is again at VDD, then I'll have current flowing here, ID is equal to twice I0 if this W by L is equal to 2 W by L of, or rather if it is W by L, then this should be 2 W by L. Okay, then in that case I will have twice I0 flowing here. Okay, it's the same logic what we had discussed earlier, and I should make sure that this drain source voltage, this drain voltage should be in such a way that the source drain voltage should be greater than the source gate voltage minus VTP of the transistor. Okay, See, finally, let me touch upon a very important idea. So essentially, I can put PMOS and NMOS current mirrors, together in a sense. This PMOS current mirror, this is a current mirror, right? And this could be actually used to build a reference current for the NMOS. Okay, so for example, if I want to have an NMOS current mirror, essentially, then I need to have this I0 as the reference current, right? So what will happen? I need to provide I0 from somewhere, and this I0 which is coming from here can be used as a reference current for NMOS current mirror. For example, let me put another transistor here and extend the VDD line. Okay, and let me say that I'll have a case where I have my source here, and then this is W by L itself, meaning it's the same W by L of this one. Okay, so that I will have NMOS, this PMOS current which is flowing here as ID is equal to I0. Okay, if I have a situation like this, I0 is now flowing here, right? Now if I put an NMOS current mirror here and make this source ground, and then make a drain feedback here, and then put another NMOS transistor here whose source is also grounded. Now these two gate source voltages are the same. Let me call it M4 and M5. They are identical NMOS transistor. And then now if this drain voltage is greater than Vg minus Vt, okay, of this transistor Vtn, then obviously I am going to have this current also I0, because this setup is a current mirror setup. Okay, and I am giving a reference current of I0 to this current mirror feedback setup. So this will generate a current of I0 as long as these two are at ground, so that VGS are the same. Okay, so I could not do this using a PMOS current mirror itself, because if I want to put a PMOS current mirror to drive another PMOS current mirror, you might be thinking that okay, this current is flowing here, this current is flowing here, why don't I use this current to generate, because this is the same current that flows here also. Okay, so you might be thinking, I could put another transistor at the bottom, and then this current can drive, say for example, if I do like this, okay, with the drain feedback, this is anyway having a current of I0, and I'll put another transistor here, and this will have the current of I0 also, right? So you might be thinking something like this. But the problem here is that the moment you put any NMOS below this NMOS, then this source potential is no more at ground, meaning this VGS is not equal to this VGS. So this will never act as a current mirror. This I0 will not be, so this ID will not be equal to I0, because this ID current of this transistor will be equal to I0 only when their VGS are same. Okay, that means their Vg is anyway at same potential, so their source should also be at same potential. But you try to put another NMOS to generate a current, for another NMOS current mirror, to drive another current mirror like this, it is not possible at all. So the reference current I0, so far I have been telling this is ideal current source, but nothing is ideal current source on an integrated circuit. So it is these kind of reference current sources are generated by, reference current of a PMOS current mirror essentially generated through a NMOS NMOS current mirror, while for an NMOS current mirror, okay, the reference current I0 can be generated by this reference current of the PMOS current mirror I0 can be generated by the NMOS current mirror. Okay, and that is how you link the PMOS current mirror and NMOS current mirror. Say for example, this I0 can be treated as having the current mirror NMOS current mirror here, the drain feedback, another transistor whose source are actually at ground, and this drain is where I have some kind of a reference current source I0, and then I have another, this maintain this VD at some place so that there is no problem. Now this is connected to this particular case. Say this I0 is not there, imagine that this I0 is not there. Now if this connected to this particular terminal, okay, then the current that flows in this direction is equal to I0. So current that flows here is also I0. So I0 is now acting as a reference current, and this ID will be equal to I0. Okay, so that is how you use NMOS current mirror as a reference current source for PMOS current mirror, and use the PMOS current mirror as a reference current source to generate reference current source for NMOS current mirror. But obviously by now you will have this very obvious question, that how this, first of all you need at least one I0 to generate any of the currents, okay, but once you have this I0, any more copies of current can be created. But then how to generate this I0 is something, a real question, which we will not be explaining in this course, but they can always be done through some kind of band gap reference circuits. Okay, there are some circuits which can precisely generate current I0, which are band gap reference circuits, but I will not be discussing this in this course. That is not the scope of the course, but then you can clearly do it. And as the name suggests, it depends on the band gap of the semiconductor. You use the band gap as a reference voltage, or band gap of semiconductor as a reference voltage to generate constant currents, okay, and they can be precisely set, okay. So here the idea or the takeaway message is that once you have this one current, you can generate multiple copies of current as the reference current for both NMOS current mirrors and PMOS current mirrors, and use one of them to do to generate the reference current for another one, okay. So I hope this is clear to you. This winds up our discussion on PMOS and different constant current feedbacks of PMOS. We will not be discussing the other two. There are 4 I said constant current feedback. The other 2 will not be discussed for PMOS, but then it is understood that you can actually pick it up, okay, and we'll move on to discuss the next important topics.